Hello! In today's video, I'll show you how to do the question answering over your own data. It becomes more and more popular thanks to the power of large language models. People start seeing the benefits of chatting with their own data and quickly pull out information they need out of hundreds of pages. In this notebook, I'll break down each step, they're on the picture here, and provide a fully functional code. So you'll see all code snippets. And thanks to the LangChain library, you can gather many different types of data. And those are example loaders. So you've got YouTube, Wikipedia, Slack messages, or Notion, or databases, like anything. And I've decided to use podcasts as example. And I've taken notes from one of my favorite podcasts, Super Data Science, with Harpreet Sahota. And if you scroll down here and go to download the transcript, you've got the PDF file with the transcript. And the solution I'm about to present you has many benefits, like I can save time, I can get only the information that is relevant for me, or even in that case, I can ask experts for advice. Let me just quickly show you that. If I go here, this is based on the podcast notes. I explain my situation. I'm an aspiring deep learning engineer. How should I start? And then based on the context provided, which in this case is the transcript itself, I've got the answers that Harpreet has given in this episode. Let's jump in. Okay, let's go. So we begin with with installing the packages. I've listed them here for you. So we need OpenAI and LangChain and several more. So we can either run this line in your bash or just pip install with requirements. They're here, so this is pretty much the same list as this one. And for the project, as the first step, we need to load the OpenAI API key and how to get it and why we need it. I've explained in the previous videos. Let me just skip over this part in this video. But we'll need an OpenAI API key for OpenAI embeddings and for querying our large language model. And as mentioned, the first step for loading PDF, it will be loading your data, and we're using PDFs. So loading is very straightforward. We just need one of the loaders. And in my case, it will be PyPDF loader. And I pass the path to that transcript and just load the documents. Okay, I was supposed to run. So that's when I load the PDFs. And now we've got the docs. And just let me show you. So length is 43, and if you see this, we've got 43 pages for this transcript, and the docs are of type LangChain documents. Like in LangChain, we've got so many different data types, but all of them by using some kind of loaders, we always convert them to this standardized document format. Okay, so then the second step will be splitting the pages, and this recursive characters text splitter is very practical because it allows us to define the chunk size, but also the chunk overlap. And this chunk overlap ensures that we don't split important sentences into two separate splits. Okay, so let's run these splits and let's see. We've got 84 splits out of 43 pages, so we actually doubled the number of splits. And let me just show you like the length of each split. I've defined 1,200 characters and overlap 200 characters. So now we've got like each page split into two smaller chunks of text. Okay, once we've got our splits, we need to create embeddings, because when we communicate with our large language models, we actually work with numbers, because computers don't understand words, they only understand numbers. And embeddings are the way of capturing the meaning, the semantic meaning of our text. If you're into natural language processing, understanding embeddings is crucial. In this step, which we take all our splits, so all 84 splits, and do vector embeddings on them, so that each split is captured into a vector of numbers, and those vectors are fairly long, like over 1,000 numbers in a vector. We see only a small part. We see only 3 numbers, but in fact, in reality, there are like 1,000 numbers. And in this explanation, you see like 3 different sentences. And my dog Rover and Fluffy, my cat, like these 2 sentences are very similar in the numeric representation, but if we talk about a car, it won't be similar, because the semantic meaning of this sentence is different. And let me just run OpenAI embeddings. And I've prepared some dummy sentences to show you the similarity search based on cosine similarity. And I did that for some sentences. So I've got 5 sentences, and the first and the second one are very similar. And then the third and the fourth one are also pretty similar. And the fifth one is not related. And so I do the embeddings for all of those sentences. And here I've prepared the function for measuring cosine similarity. And if I run it, you can see. So first, I've separated cosine similarity for the first and the second sentence, which, like I mentioned, are very similar. And then the third and the fourth one, which are also similar. Those first 2 examples for the first and the second sentence gets a similarity of 0.9, but then this cosine similarity gets smaller for the sentences that are not close in a semantic meaning. Let's move to the step 4, which is vector databases. We need to store our embeddings. So we haven't embedded our splits yet, but right now, so these are our chunks. So these are the splits that we've had, and we want to embed them and store in a vector database. So that way we will keep like the numerical representation of our splits in a vector database. And we will use the Chroma database, vector database, but LangChain offers like at least 35 different vector databases. My Chrome, this is how where I define my directory where I want to store it, and I've got this Chroma folder here. And after I run, I'm creating a vector database, and I will use the splits that we've generated, embedding, which is our OpenAI embeddings, and disperses directory. That's what we pass to our Chroma vector database. And when I run it in Chroma, we've created this SQLite database, and that's where we've stored our embeddings. Okay, so let's move to the next step where we retrieve relevant documents. And again, I'm using this line only because our vector database is already defined, but in case you run this notebook again and you've already run this cell and you've got your vector database here, it means like your vector database directory isn't empty. You can just load it again with this Chroma and then this persist directory, which we've got here, and the vector embeddings. So that way I've got our vector embeddings again. And let's see it in action. So what we'll do, we'll run our query and embed it and try to find the most similar splits that are relevant to our query. So let me just run it. So I write, give me all books from the episode. And I've already got it. And in the docs, I see like all the documents. So all splits that are somehow similar to our question or our query. And in our query, I mentioned books, so the semantic meaning of my query includes books, and I'm returning 5 documents, like 5 most similar documents. And if you read through those documents, like the most similar includes the manga guide to calculus and the manga guide to linear algebra. And like there is like deep learning illustrated guide. So, you know, based on this query, our vector database returned the documents, like the splits that seem to be relevant to our query. And let me use this cosine similarity again to check how similar the answers are to our question about the books. And as you can see, LangChain returns the documents from the most similar to the least similar. And the first one is fairly similar. The second one, like this number is quite high. This one is smaller, and those are way smaller, but still somehow relevant. So let's move to the last step, which is generating the answer. So again, we've had our query and we found the most similar answers, and the vector database returns the chunks of split. And the vector database returns the most similar chunks of text. And then we take them and feed them into our large language models. So that's how we provide context for our large language model. We will use retrieval QA from LangChain, and we'll need to define like our large language model, our prompt. The prompt is here. So I'm just informing my large language model, my GPT 3.5. I will provide you pieces of context to answer the question. And what I actually do, so this is my query, my question, and from the vector database, I get the relevant pieces of context. And that's what I'm going to feed to my large language models, to my large language model. Let's just run this cell first. And our QA chain from retrieval QA uses the large language model, which is GPT 3.5. Retrieval is our vector database. I'm not explaining what this does, and I want to return the source documents. So to see which documents actually went to our context. And then I'm just using this template to prompt our GPT 3.5. So I've run this cell, and let's see what I get from this query. I'm an aspiring deep learning engineer. How should I start? And I'm running this query. Okay, and I've got the answer based on the context I've provided. So based on the context provided, here is the helpful answer. To start your journey as an aspiring deep learning engineer, it's recommended to follow a top-down approach, which is great because if we go here, top-down, I know you have a particular philosophy of learning deep learning that you describe as top-down. And that's where Harpreet explained actually what he means by this top-down approach. Based on those answers, here are some steps. Start exploring applications of deep learning, such as computer vision. Okay, and this top-down approach. This means focusing on applications and particular implementations rather than getting overwhelmed with the mathematical details initially. So again, I think that's what Harpreet skip the math. Yeah, that's what Harpreet says, skip the math. Using this query, we've got some relevant documents that actually answer the question that we've asked. So let me just run this result. Source documents, and we've got 4 documents. Yeah, so these were the most relevant documents to our question. Where I'm heading here is like with those resource documents, we use only 4 chunks of text out of 84. If you remember, we've got 84 splits of we've got 84 chunks of text based on the podcast transcript. But to answer this question, to answer my question from here, we've used only 4 documents. It means we've used only 4 chunks of text that are the most relevant to my question. So let's try with another question. List, or maybe query, list all books. And let me just run this, and look, the manga guide to calculus, the manga guide to linear algebra, deep work by Cal Newport, deep work by A Visual Approach by Andrew Glasner, and deep learning illustrated by John Cron. And if I go to the podcast notes, it says items mentioned in this podcast, and look, deep learning illustrated by John Cron, deep learning, a visual approach by Andrew Glasner, the manga guide to linear algebra, the manga guide to calculus, deep work by Cal Newport. Okay, so this one is a mistake, but I think the LLM got confused by this by Daniel Berg, because that's usually how we talk about books, like Deep Work by Cal Newport, Deep Learning by Andrew Glassner. But we've got all the books mentioned in this episode. And again, if I run this, we've got this answer from our GPT model based only on 4 documents. So it's like only 5% of the whole transcript that we've used to answer this question. Yeah, and if I want to, I can just see how similar are those documents. So I'm taking these documents, these chunks of text, and just compare the cosine similarity, I calculate the cosine similarity to this query. And again, we've got them in the decreasing order. So that's it for today. In the notebook itself, I've added this bonus section where I talk more about the theory of vector databases and understanding the context length in large language models. So feel free to check that out. And I highly encourage you to experiment with your own data. All you have to do is actually to change this part. So if your data is in the PDF loader, you just if your data is in PDF, you just change the path to your data. And if it's in a different form than a PDF, you just change the loader and use it instead. But from there, like each following step will be the same. And feel free to grab this whole notebook. It's on my GitHub. You'll find the link in the description. You can expect more of this kind of content on my channel. So if you're interested in building projects with LangChain, with large language models, make sure to like this video and subscribe and hit the bell on my profile so you always get notified. And thank you for today.